Hello and welcome to our Design Day video. We are Team 21018 and we are the Safe Route Clarity project. Our sponsors are ACSS, which is an L3 Harris and Thales joint venture, and our mentor is Catherine Merrill. My name is Ryan Hammond.
I'm Brian Volpe.
Abraham Arroyo.
I'm Stan Hurley.
I'm Nicholas Hammond.
I'm Joshua Reck.
I'm Tristan Newbury.
On this slide, you'll see what is an aggregate of our slides. Because of COVID-19, we weren't able to have an actual poster, so this is the substitute. So an introduction to our problem. Today's pilot displays are incredibly cluttered with numerous aircraft in dense airspaces, and this is especially prevalent during takeoff and landing. In order to combat this problem, we used machine learning in order to predict adjacent flight paths and then filter out irrelevant aircraft so that way the pilots can see.
Here's the concept of operations. Our primary stakeholders, as stated before, was ACSS. It's an L3 Harris and Thales joint venture. Our system boundaries were within the avionics system of an aircraft, and our system would be used in an aviation navigation multifunctional display, or an MFD, by pilots or aircrafts. It's explicitly software-based. Our system constraints were computing power and computing time. Here are the system requirements. As you can see, PAN 1.0 is data for requirements. PAN 2.0 is machine learning. And there are the three different machine learning algorithms we use. Next, PAN 3.0 is our comparison and filtering requirement, and PAN 4.0 is our output to our user. Next is the system requirements flowdown. It shows the system, the subsystem, and the subcomponents.
Pictured here is our system block diagram. Outside of our system, we have flight data that was provided to us. Inside of our design system, we have three main subsystems. We have the data formatting system, where data is formatted and accepted. We have the machine learning subsystem, where the actual flight predictions occur from our machine learning algorithm. The next subsystem is the comparison and filtering subsystem, where the predicted courses are compared to our own ship. Team 21018 utilized the agile methodology commonly used by software engineering teams by working on three iterative approaches to explore, test, validate, and deliver our three algorithms. Our team did this by delegating large tasks, known as epics, into smaller chunks and reviewing our progress after each 2-week sprint. After each sprint, we would then debrief, analyze our progress, and redelegate tasks and priorities in order to complete a large task or a large epic, such as an iteration status review. This is our system verification plan, which follows the critical path we took in verifying our requirements in order to verify and accept our system. Our algorithm verification test procedure is as follows. For each algorithm, we tested the best models by analyzing their mean squared error, R-squared coefficient, and root mean squared error. If the prediction was not within tolerance, this prediction would be discarded.
Our overall design process consisted of three iterative deliverables. In our first deliverable, ISR1, we focused primarily on the system requirements, including the system architecture, machine learning algorithms, and our trade studies on those algorithms. After confirming the scope of our project with our sponsor, we began working on the first machine learning algorithm and verified that it predicted flight positions within our expected tolerance. In ISR2, we worked on our second algorithm and explored different visualizations to graphically display what the algorithms are doing. Lastly, in ISR3, we completed working on our third and final algorithm and worked on the statistical analysis of the three different algorithms to verify which one worked best. Shown here, we have our indentured document list showing the different design documents that we came up with to verify the scope of our project.
Next, we'll be going over the delivered product. Here we have some images that show off the delivered product, where algorithm 1 is on the left, the red line is the actual flight, and the blue line is the predicted flight. Here we can see that the red line and the blue line are pretty close, but they're not entirely on top of each other. In algorithm 2, well, it cannot be easy to see here, but the red line has a bit of a corner that comes in, and where that blue line gets a little inaccurate. And then with algorithm 3, while there's a lot of blue going on here, it stays tightly around the red line, and we infer that this algorithm is going to be the best going forward. Next, we have our acceptance test data sheet, where this is a sheet that we used to verify that we completed a requirement with testing, where we show that the test was completed with the required value under tolerance.
This here is an overview of our requirements for the delivered product. As you can see, we started with PAN 1.0. That includes the input of data and filtration component. Began by creating the input mechanism that takes in a CSV file and reads the content into the internal program. Data will contain the flight data that was recorded by our sponsors. The filtration component will then parse this data of the CSV file for algorithms to perform the desired functions. We continued on to PAN 2.0 to construct the machine learning algorithms. Each of the algorithms were verified by analysis. You can see in the column to the right the resulting values to use for comparisons between each of the algorithms to determine which is the most efficient. Each of the values fell within the required mean squared error margin, and algorithm 3 was one that performed the best.
Because of time constraints, we were not able to complete PAN 3.0 and 4.0. PAN 3.0 was postponed to focus on testing and comparison, and PAN 4.0 was out of scope and was added in just in case we had the time to finish it. Path forward for ACSS and L3 Harris to continue work on this project is to create a filter to compare ownership and building a test simulator to put the machine learning algorithms to the test. Lessons learned are to test early and test often, task delegation, using sprints and story points, expect the unexpected, and update documentation frequently. For deliverables, going back to last semester, we had the proposal and ISR1, which were both completed and delivered on time. This semester, we have had ISR2, which was completed and delivered on time. And that brings us to ISR3, which we are wrapping up work on, and it is on track to be completed and delivered by the deadline. For our summary, we have that MFDs are highly cluttered inside aircraft cockpits. With the help of the machine learning algorithms, we can predict path of the aircraft and use this to filter out some of the more irrelevant aircraft. Our machine learning algorithms were heavily tested and show promising results. And we believe that given the high accuracy of our test results, these algorithms can be used to help private and commercial pilots. Thank you for your time, and we'd like to take this time as well to thank our sponsors, John and Jay, and our mentor, Catherine, for everything they've done for us this semester.